Okay, boys and girls, ladies and gentlemen.
It's a poser.
It's not. It was a poser, but we solved it.
Excellent.
That's Mr. Duggan. He said excellent. He also said it's a poser. Okay, so what I want to do right now is derive the range equation from the first principle. Okay, so we're going to launch something at some velocity with some angle like this, right? Okay. Now, I think we've solved enough of these, which is more than one, I think. Yes? I think we've solved 3. Oops. We've solved 3 of these, okay? And I think that we all know that the range ultimately is going to be the horizontal velocity times the time in the air. Yes? Okay? So it's going to be the horizontal velocity times the time in the air. And the horizontal velocity is easy. The horizontal velocity is v cos theta, isn't it? If v is the hypotenuse, then this side is v cos theta, right? So our formula becomes v cos theta times the time it's in the air, right? Now, how did we find the time that it's in the air? Well, remember we used vi equals whatever, didn't we? This thing, right? Okay. Ultimately, this is what it ended up being. And I don't know if you've recognized this yet, but the time in the air is just twice the initial vertical velocity over g, where g is 9.8. Isn't it? That's what it ends up being. I mean, I just do that, right? Because you end up going this guy plus this guy, don't you?
Yeah.
That's what the math ends up being, and then you divide by 9.8. Right? So if I substitute that, and then vi is just v sine theta. Yeah? Right? So the time in the air is 2v sine theta. I think this room can barely contain the excitement. We're deriving an equation, and you guys are like, yes? And then what next? Oh yeah, I think you should know. I'm just deriving something for you. Okay, I want to show you where it comes from. So all I'm going to do is I'm going to take this and stuff it in right there. No comments, please. Okay. Cos theta times 2v sine theta over g. And we have our formula, but we're going to make it look cooler than that. So I can take the v times the v and do what? V times v is v squared, right? And so ultimately this becomes v squared over g sine theta 2 sine theta cos theta. Right? And that's our formula. But wait, there's something more we can do. Because isn't 2 sine theta cos theta something? Did anybody take that class? Does anybody know what 2 sine theta cos theta is? Does anybody have any idea what 2 sine theta cos theta is? 1. I hear 1 is being guessed. No. That's sine squared plus cos squared. All right. I know. Okay. Who wants to join the Navy? 1, 2, 3, 4. Here we go. 1, 2, 3, 4, 5. 1, 2. Navy knows what's good for you. 1, 2, 3, 4. You need one more? Oh, I'm so sorry. Who didn't? 1, 2, 3. Now, I'm not just shamelessly promoting the Navy. I am related to a retired rear admiral. I am related to a retired rear admiral, but I'm a pacifist, a liberal pacifist, but I'm a pro-Navy liberal pacifist. Okay, you got that? I'm not just shamelessly promoting the Navy. The trigonometric identity that we need is on this sheet. So flip it over. Trigonometric identities. You see that on the back side? What is 2 sine theta cos theta? Yes. Sine 2 theta. It's the double angle theorem. Now, if you never took trigonometry, class, if you never took trigonometry, I just said, okay, which is just fine, but we're going to substitute 2 sine theta cos theta is the sine of 2 theta. So this is our range equation, is v squared over g sine of twice the launch angle. Now, if I put 0 in for the angle, sine of 0 is 0 and it goes nowhere, correct?
Yes.
If I put 90 degrees for the angle, what am I doing? Which way am I shooting? Straight up. The range should be 0, and of course, twice 90 is 180. Sine of 180 is also 0. And if you don't believe it, put your calculator in degrees, try it. It's 0 because you're back to 0 on the unit circle, right? Okay, so this thing works, and then of course the very best angle is what?
360, 45.
45 degrees is our best angle, right? Okay, so we put 45 in there. Sine of twice 45 is sine of 90. Sine of 90 is 1. That's as big as sine ever gets, is 1. I know it's very disappointing.
Can we put in the angle that we're solving for in the sine part?
Yeah, well actually right now we can calculate where this is going to land. So everybody take your calculator right now and just type this. Just type, what was our velocity? Our velocity was 10, wasn't it? Right? We don't need to break it into components, right? So we go 10 squared divided by 9.8 times sine, left parenthesis, 2 times 40, right parenthesis. Type this into your calculator. See what you get for the range. If you are in degrees, there we go, 10.04. Is that what it is? Yeah, there you go. Okay, that's essentially what we got. We were a little off because we rounded, but that's okay. 10.0 is what we're shooting for. That's kind of cool, isn't that cool? Yeah. So, not only on your two-dimensional motion sheet, now, boys and girls, not only do you know how to do 4 through 6, you also know how to do all of these range ones, right? So on one of these I say the angle and the speed, angle and speed, angle, speed, find the range. That's using this one. And then we've already used this other one in the rocket competition, solving for the angle there, right? So the other ones say what angle do you use? And notice it says angles. And that's because if you get, say, 20 degrees as one of the answers, the other answer is, I don't have any.
You don't have it like at all?
Yeah, I'm sorry.
Do you have the folder at least?
I don't.
Okay, all right,
I'm
thank you.
sorry. Yeah, so if 20 works, 70 also works. So find the angle complement on there. And if you can't remember that, write that down there. That's fine. So I've done that. The only thing you haven't learned how to do is 7 through 9, but you can do 4, 5, and 6. And so when I'm done doing my demos, we'll just work on 4, 5, and 6, which are more arc trajectory problems.